Hi, dear students. This video record is about fatigue failure, and how the tools of inventor can be used for finding the technical life of a component. Okay, let's start. I have a presentation about fatigue failure. Okay, then after the lecture part, then focus the attention to the things to do in CAT environment. Okay, what is fatigue? In English we say fatigue, in Turkish malzeme yorulması. The progressive deterioration of the strength of a material or a structural component during service such that failure can occur at much lower stress levels than the ultimate stress of material. Yeah, say that phenomena is called fatigue. In other words, when loadings are repeated n times, in such cases, fracture will occur at a stress much lower than the static breaking strength. Yes, this phenomenon is known as fatigue. Well, from the famous stress strain diagram, in the figure, well, it is the diagram for a ductile material such as steel, aluminum, etc. Yes, the ultimate stress, and we have yield stress and fracture stress. Well, if the load is static, well, such curves, under laboratory conditions are output, well, loading the specimen statically. Increase the force, but not quickly, very slowly increase the load. Well, consider very approximately, very accurately, the loading as static loading. But if the load is not static, but dynamic, means the magnitude of the load is not constant. It is changing, and also, it may be the case, not only the magnitude, but also the sense of the load may change. If the sense and also the magnitude of the load are changing, then can say that in terms of fatigue, it is the worst case. Okay, in time, depending on the magnitude of the stress within the body, okay, the duration time, that is say that the technical life for the component or for the structure may be even in the order of seconds. Okay, if the load, in other words, is dynamic, then we need to consider fatigue. Okay, don't say that stress is less than yield limit, less than ultimate limit, so there will be no risk. The component can be used. No, it is not true. Unexpectedly, the component may be broken. Fatigue is a dynamic phenomenon that initiates small micro cracks in the material or component and causes them to grow into large cracks. These cracks, if not detected, cannot be seen, can lead to catastrophic failure. Fatigue is classified into 5 types. Cyclic fatigue, it is the most common case. Object is under the action of a loading, cyclic load. It changes is magnitude and or it is sense, periodically, okay, caused by repeated loading and unloading of the material or structural component. The other fatigue is quite important if, in the phenomena there is a heat transfer, temperature is not constant, it is changing because there is a heat transfer from the surroundings to the system or vice versa. The heat transfer may also be transient. Temperature is changing in time. So if the thermal expansion of the material is not allowed because of a certain limitation, there may be a rigid component and it prevents the other component from expanding. Then, within the body, there will be, loading because of such a prevention. If the body cannot freely expand, then there will be undesirable stresses within the body. It is called thermal stress. If the temperature is not constant, it is decreasing, it is increasing, then the stress correspondingly will decrease periodically. So stress is not constant within the body, it is changing in cyclic changing. So the result will be fatigue. This type of fatigue is called thermal fatigue. Okay, acoustic fatigue, yes. Sound waves, noise waves can exert, cyclic loads onto a body. So changing pressure in sense in magnitude caused to fatigue. Yes, sonic fatigue is caused by fluctuations due to vibrations excited by for example, jet or propeller noise. The other fatigue, corrosion fatigue, seldomly may be the case to deal. Cyclic fatigue accelerated by surface corrosion of the material penetrating inwards. Threatening fatigue, I didn't highlight this type of fatigue. Seldomly it may be necessary to consider. Threatening fatigue caused by small-scale rubbing and abrasion of adjacent parts. The most common fatigue is cyclic fatigue, thermal fatigue, and also acoustic fatigue. Okay, when loadings are repeated thousands or millions of times, in such cases, rupture will occur at a stress much lower than the static breaking strength. Yes, as at the beginning already mentioned, this phenomenon is known as fatigue. Okay. A fatigue failure is of a brittle nature. Abruptly, suddenly, it may occur if, of course, the little cracks cannot be distinguished, cannot be seen. Fatigue failure is an important phenomena to consider not only for brittle materials but also ductile materials. Fatigue must be considered in the design of all structural and machine components that are subjected to repeated or fluctuating loads. The number of loading cycles that may be expected during the useful life of a component varies greatly. For example, a beam supporting an industrial crane may be loaded as many as 2 million times in 25 years. It may be the economical life. and also if fatigue failure has been considered in designing the object, may also the technical life. Well, how can find the year? Well, we know knowing the number of cycles. But if you know that, for instance, an industrial crane is used per day, working day, let's say 300 loadings. Well, we are using the crane, okay, to lift and to transport a load, heavy loads. It is used how many times per day? Let's say 300 times. Okay, this means per day we have 300 cycles. How about the technical life of the crane? Let's say million cycles. Okay, million divided by 300 cycles corresponds to the number of years. Can say that that object can be used in such a period of time. So, in converting the number of cycles, yes, if the number of cycle is less than that threshold value, then there will be no fatigue. But if the number of cycles is equal to or greater than that number, then the result will be fatigue failure. Object will be broken. You know this. Number of cycles can be converted to days, weeks, months, years. If you know the period of the loading, for the object in consideration, then just by dividing the total number of cycles, okay, to the number of cycles per second while the object is being used, it is loaded cyclically, then yes, can find the life duration. Not in cycle, but say using the time unit, maybe days, weeks, months, or years. For instance, an automobile crankshaft will be loaded about 500,000,000 times if the automobile is driven 200,000 miles. Okay. If the threshold value, the total number of cycles for a crankshaft, okay, is less than the threshold value. What is the threshold value? I'm going to talk about it in a few minutes. Then can say that okay, that can be used safely, securely. There will be no fatigue failure. But if it is exited, then unexpectedly crankshaft will be broken. Okay. The number of loading cycles required to cause the failure of a specimen through repeated successive loadings and reverse loadings may be determined experimentally. Yes. Well, the characteristic for the material, the characteristic is determined under laboratory conditions. Well, loading the object, okay, periodically, we determine the limit. What is that? Say that endurance limit. If the endurance limit, if the stress is greater than endurance limit, it is there is no doubt. At a certain time, fatigue will occur. If the stress within the body at any point, all the points, less than the equals or less than the endurance limit, then can say that although the loading is a dynamic load, there will be no fatigue failure. Yes, in this figure, for instance, as an example for one type of steel, it is called as 120, 1020, sorry, HR. Well, if the stress, well, take a pen or pencil. For instance, if the stress of the object at any point is equal to that much, then, well, the maximum number of cycles, okay, for the load it is exerted onto the body will be equal to that much. Okay. Well, to this cycle, up to this cyclic loading, well, there will be no fatigue failure. But if the technical life, well, this is the technical life actually for the component. If, well, the object is furtherly used, okay, although it reached to its technical life, the limit of technical life, then, well, not in this order, but, well, the number of completely reverse cycles greater than this one, then the result will be fatigue. Okay, if we decrease the stress, then you see technical life correspondingly increases. But there is a threshold value, you see. Well, if the stress is in this order, then not a matter, well, if the stress is in this order, you see, well, since this part of the curve, which curve? Stress and number of cycles curve. It is called commonly sigma n curve. Sigma n curve. Okay, well, if the stress is at that level, then can say that, well, it can be used till it is economical life. Technical life, because going to be unlimited. You see, well, if the stress is less than 30 ksi, here the unit is British, kilopound per square inch, well, the technical life, you see, this, well, it goes to infinite cycles. This means, well, it can be used unlimitedly. There will be no fatigue failure, in other words. Well, such a limit is called endurance limit. Okay. Endurance limit is the stress if within the body at all the points the stress is equal to or less than this limiting value, then can sure that there will be no fatigue failure. But if the stress set by the applied loads is greater than this limit, then it is unavoidable. There will be fatigue failure. When, for instance, if the stress is 40 ksi, then the fatigue failure will be after this time. Well, here in the graph we have the total number of cycles, the number of periodic loadings. Well, depending on the speed of the object in consideration, this total number of cycles can be converted to daily lifetime unit, days, weeks, etc. For instance, it is the load periodically applied onto a body per day, for instance, one time. Okay, well, this total number of cycle 100,000. Yes, 10 to the power 5, 100,000. This means if the number of cycle, okay, for the load, it is applied onto the body is 1 per day, then can say that that object can be used 100,000 days. After such a period of time, fatigue will occur. Of course, if the period of the loading is not 1 per hour or per day, but say that, for instance, per day the number of cycles is 100,000. If the object is loaded, well, dynamically 100,000 times per day, well, since the technical life, this limiting value is the same, can say that that object can be used only for 1 day. So, well, in converting the number of cycles to a time duration, well, we should know the period of loading for the body, or the speed of say, the component corresponding to the frequency of the load. Okay. Well, in general, for most of the materials, well, the sigma anchor will be in such a characteristic. Along the vertical axis, we have the stress value. Along the horizontal axis, we have the number of cycles. If the number of cycles is exceeded, or if the object is used, attempt to be used furtherly, then no doubt fatigue will occur. If the stress is equal to ultimate stress, then how many times the load can be applied onto the body? 0 times. If the stress is equal to ultimate stress, then, well, even for the first attempt, the object will be broken. Okay. If the stress is decreased, then, well, the technical duration increases. Well, this region, of course, such a stress value, material will be in plastic region. Okay. Well, this point is the point. The stress value corresponds to yield limit. Okay. Well, if the stress is equal to the yield limit, then, well, correspondingly can say that if this total number of cycles exceeded, then object will be broken because of fatigue. Furtherly decrease the stress, then you see technical life, total number of cycles, it is the limit. If it is exceeded, then fatigue will occur. Increases, and from this graph perceive that, of course, if the stress is equal to yield limit or less than the yield limit, well, okay, while the object is being used, it will deform, elastically deformed, elastic region. Okay, and from the graph see that, well, if the stress is equal to that much or less than this order, then there will be no fatigue. The technical life of the object for the given material and loading type will be unlimited. Infinite life region is this region. Well, from this graph, see, well, the endurance limit, that stress value is even much less than the yield limit. I mean, if the loading is dynamic load, don't say that, yeah, well, the stress is, von Mises stress is less than the yield limit, so, well, there will be no failure. No. But it is true for static loading, but if the loading is dynamic, that is not true. Well, if the stress is less than the endurance limit, then can say that, yes, there will be no fatigue failure. I have already talked about such things. Examination of test specimens of, say, shafts, springs, other components that have failed in fatigue shows that, well, the failure was initiated at a microscopic crack or at some similar imperfection. At each loading thereafter, the cracks was very slightly enlarged. During successive loading cycles, the crack propagated through the material until the amount of undamaged material was insufficient to carry the maximum load, to balance the maximum load, and an abrupt, brittle failure occurred. Okay. Well, surface quality at this point is quite important because fatigue failure may be initiated at any crack or imperfection. If the surface has not been polished, then well, fatigue endurance limit will be well greater, greater for such an object. The surface condition, I mean, of a specimen has an important effect on the value of the endurance limit obtained in testing. The endurance limit for machined and polished specimens is higher than for rolled or forged components with rough surfaces. Or if over the surface we have corrosion, it is also maybe the case, endurance limit will be greater. Okay. And yes, now how much the endurance limit? No doubt it is less than the yield limit, but what is the value? Actually, the question is correct answered performing fatigue test. Okay, but say as an average, can say that the fatigue strength of a material is the maximum stress that can be repeated for a specified number of loading cycles without producing failure of the structural member. For steels with tensile strength less than 200 kilopound force per square inch, can say that endurance limit is almost equal to the half of the tensile strength. If the tensile strength of the steel is greater than 200 KSI, kilopound force per square inch, can take the endurance limit as equal to, as an average, 100 kilopound force per square inch. For wrought aluminum alloys, the endurance limit 40% of tensile strength. For cast aluminum alloys, endurance limit can be taken as almost 30% of tensile strength. Okay. Now, after talking about such things, then also say it is related, the topic related with dynamic loading. If the load is a dynamic load, yes, need to consider not only fatigue failure, endurance limit, technical life, but also resonance. Okay, module analysis. If the object is under a dynamic load, then well, this is important to know and also check. If the frequency of the load becomes equal to the natural frequency of the object for any object, any structure, yes, it is defined. We talk about natural frequency. The the natural frequency depends on the shape of the body, and also the elasticity of the material, stiffness of the material of the object, and also well, the mass of the object. Well, natural frequency can be expressed or calculated using this expression. It seems as simple to calculate, but it is not true. Well, in the square root, K is the stiffness value, but equivalent stiffness, equivalent spring constant. Well, for the structure, for the component, be able to calculate the equivalent spring constant. Well, the equivalent spring constant depends on the shape and also the elasticity of the material. The other term at the denominator is the mass, but it is not the mass of the object. It is the equivalent mass. To be able to calculate equivalent spring constant and equivalent mass, well, yes, well, it is recommended. Enroll to a course. It is about mechanical vibrations, for instance. Then in the content of that course, it is deeply studied how the equivalent spring constant and equivalent mass are determined. Okay, well, divided by 2 pi is the frequency. Which frequency? Sub n, f sub n highlights that natural frequency. If the frequency of the loading becomes equal to the natural frequency of the body, then we say that we observe that in such a case, the amplitude of the oscillation tends to go to infinity. But thanks to the existence of the dissipation set by friction forces, caused by friction forces, viscous forces, where the amplitude of the oscillation of the body cannot go to infinity, but it may reach to such a very great value. If the amplitude is too much, the oscillation deflection is too much, then of course atomic bonding forces may not be sufficient to balance the stress value, and the material resultantly will be broken. Avoid having resonance. Well, select the frequency of the load. Well, for instance, why the object is under the dynamic load, because it is driven by a motor, and motor oscillating because of some unbalanced materials, excessive runouts, where the shaft is vibrating. Well, such an oscillation is transmitted to the structure of the mechanism. So, if the turning speed of the shaft, the frequency of the shaft, becomes equal to the natural frequency of the mechanism, then mechanisms start to oscillate with very great amplitudes. That phenomena is called resonance. If resonance occurs, the result, most of the cases, will be failure. Okay, so, well, need to determine the natural frequency, not only one frequency. For a certain body, well, we can see that object has more than one natural frequencies. After finding the spectrum of natural frequency, then knowing the natural frequencies for the component, well, we must select the frequency of the loading, for instance, the speed of the driving motor, well, as the one, it is frequency must be different than the natural frequency object. Okay, well, in Inventor, in Fusion, we can find the tools, calculation tools. These are for outputting for finding the natural frequencies of the body's components. Well, such an analysis, it is the analysis to determine the natural frequencies of the objects, is called model analysis. Model analysis helps to determine the vibration characteristic, natural frequencies, and model shape of a mechanical structural component, showing the movement of different parts of the structure under dynamic loading. If the loading is dynamic, then yes, we must consider the resonance, natural frequencies, and prevent resonance. Okay. Yeah, yes, in structural engineering, model analysis uses the overall mass and stiffness. Yes, equivalent mass, equivalent stiffness. Okay. These periods of vibration are very important to note, for instance, in earthquake engineering. If the natural frequency of the building becomes equal to the frequency of the earthquake, then the building will start to resonate, and probably the bonding forces of the material or the structure of the building won't be sufficient to balance the stress values, then the object will be broken. Okay. For a particular input, like an applied load of certain amplitude and frequency, what are the limits of the system's response? For example, when and what is the maximum displacement? Every object has a natural frequency or resonant frequency at which the object can naturally vibrate. There are several examples where a prior accurate model analysis could have prevented loss of lives and property. Some famous ones include, for instance, Tacoma Narrows Bridge disaster of 1940. The Tacoma Narrows Bridge was built in the state of Washington, USA on November 1940. At the time, November 7th of November, around 11 a.m., the bridge came down instantaneously, failed instantaneously, destroyed. A later investigation revealed that the cause of the collapse was aeroelastic flutter. It was a wind-induced collapse. While wind loaded the bridge dynamically, the winds were blowing at a particular frequency which happened to coincide with the resonant frequency of the structure of the bridge, resulting in the sudden collapse of the structure. Yes, the bridge destroyed, instantaneously came down. Well, there is a video film here. Well, I'm not so sure can play. Well, I think stop the show. And then, yes.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest...
Sorry. With the wrong click, I stopped the play. Then do it again.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. the actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Yes, by that time, actually, the engineers, constructors almost had no idea about resonance. But after seeing such a catastrophic failure, then deeply investigated the phenomenon, deeply investigated, and thereafter they concluded that it is because of that reason. Well, when the wind frequency becomes equal to the natural frequency of the bridge, yes, resonance will occur and the object fell down. To be able to prevent the famous building, Burj Khalifa, it is one of the highest, tallest buildings, has been constructed, Burj Khalifa in Dubai. To be able to uh, have the natural frequency of such a building, such a structure, differ than the earthquake frequency and also the frequency of the blowing wind. One of the things to do is that, what's that? At the bottom of the building, foundation of the building, using some strong springs, well, change the equivalent spring constant for the building for having the natural frequency differ than the frequency of the wind and also the frequency of possible earthquakes. It might be done, but using such elastic elements at the foundation, then there will be a very great oscillations at the tip of the building. While the designers concluded that it is not a good idea to increase the spring constant, they found the other solution. They selected the other way. Change the equivalent mass. For changing the equivalent mass such that the natural frequency of the building will be different than the earthquake frequency and frequency of the wind, as it can be seen from the photograph. They gradually decrease the weight of the building from foundation to the top point, highest level. Another interesting case, in 1985 in Mexico City, earthquake unfortunately occurred. During the earthquake, most of the 6 to 15 floor buildings collapsed, resulting in huge loss of life and property. Interestingly, buildings with less than 6 or more than 15 flats, 15 floors, stories, were not damaged as much, while buildings with 9 stories, 9 floors, were completely destroyed to rubble. Two explanations were offered for the earthquake's impact: the duration of the shaking and the resulting resonance with the lakebed frequency. In other words, while the destroyed ones, destroyed buildings, well, resonated because their natural frequencies unfortunately became equal to the earthquake frequency. Okay, the resonance frequencies of the 6 to 15 story structures coincided almost exactly with the frequency of the earthquake. Okay, now dear students, well, I think it is going to be more convenient for you. After talking about such things, then let's have a break. And after the break, I'm going to talk about how fatigue analysis is performed in Inventor, how the model frequencies can be determined using the tools of Inventor or using the tools of Fusion. In the next video record, yes, it is going to be CAT application. In CAT environment, demonstrate how can check and determine the technical life of a component, whether there will be fatigue failure or not. Okay, talk about such things.